STAT340 Week 10. So let's look at the content this week. We are now turning to classification problems. We have to say a little bit of that also in STAT340 and how the data look like mostly. Then few words about what is known as the base classifier or base rule for classification, because this is sort of a fundament for the method we are talking about today. So this is a little bit theoretical, but I'll try to make it understandable. Linear discriminant analysis, that's the main method we are looking at this week. It also has a sort of a cousin called quadratic discriminant analysis that we also sort of, you get it when you buy LDA, you get QDA as well. You could say, so because they are almost the same thing. So it would be strange not to mention it. Measures of goodness, that applies to all classification methods, confusion matrix and accuracy and so on. And we will see a little bit about cross-validation, especially when it comes to, we will use it for variable selection, because that's something we have talked about in previous weeks, actually all throughout this course almost. Which variables, which predictor variables are the important ones, right? And this is really important if your focus is to sort of understand the data or understand the phenomenon that the data comes from. So classification is, at least this way of classifying is mentioned in chapter 25 in the R book, but not very much. So I would recommend, if you really want to get a good introduction to this, look at this book here. I mentioned this already in week 1. This is also a free book that you can download and use as a sort of support. In chapter 4 of this book, you have an excellent introduction to this topic, I would say. Much better than the R book. Okay, but it's a little bit more mathematical, but if you are not completely unknown to the mathematical notation, this is a much better introduction. So, classification problems, what are we talking about here? First of all, data. So again, let's say we have data case number I, which is some response yi and some predictors xi, right? And we have p predictor variables. We have n data cases, so this is just one of them. So we can again think of it as a data table, right? Where the response is one of the columns and the predictors are all the other columns, or not necessarily all the others, but some other columns, right? So it's sort of a data table, everything, right? And the index I now refers to row number. So data case I is row number I, right? Either 1, 2, 3, 4, so on, down to n. There are n data cases, n rows. And this is how data have been looking like all the time, right? We always have data in tables. So when we talked about regression problems, the response is quantitative. The y here is quantitative. It's numerical, right? The predictors are also typically quantitative, but maybe categorical. So the predictors are usually quantitative, but we may have some categories in here, categorical columns, right? We saw this ANCOVA, analysis of covariance, where we mixed both quantitative and categorical data. When we talked about ANOVA, the response was still quantitative, this one, but then the predictors are only categorical. Whether it's fixed models or mixed models, ANOVA are always categorical. And the same regression can also be fixed or mixed models, of course. So what we are turning to now is another sort of type of data where the response is categorical, because that's something we haven't really seen up here, right? The response is now categorical with C classes, we say, and that is actually the factor levels, right? So this one is now categorical, and it has capital C factor levels that we call classes now. The predictors can be both quantitative and categorical, just as for regression. So this classification is sort of similar to regression in the sense that the X matrix here, or the data over here, are of the same type more or less. But the only difference is that the response now changes from being quantitative to categorical. And this happens in quite a lot of cases, you could say. In many studies, the response that we measure is not a numerical variable, but it's simply categories. Classification versus clustering. What is the difference? Because we talked about clustering already very early in this course. Well, there is a big distinction actually. Clustering means we search for groups in the data. So we sort of search for categories, you could say, grouping of the data. But the point is we have no prior knowledge of which groups or how many. So this is explorative, right? We explore our data to see how they look like. And that is also why it's called unsupervised learning, this clustering and PCA and these type of methods is unsupervised. We talked about this earlier. While classification, in the classification situation, groups are already defined, right? They are defined. There is no exploring here. We know exactly how many groups, and actually also the groups themselves are sort of defined. So we have some prior knowledge about the world that we are studying. And we now want to model how grouping is explained by our predictor variables. It could also be that we only look for predictions. Very often that's the case. But in STAT340 we will try to sort of lean more towards this motivation here, the explanation, right? Because prediction is sort of data science. And this is what we call supervised learning then. Because we have this prior knowledge, it's supervised by this prior knowledge. So, so this is, we already know which category the different responses belong to. Right? So classification problems are often motivated by prediction, right? Data science. And I think if you take data science courses, you will hear a lot about classification, much more than here. We just touch upon it here. So this is a big thing in data science, perhaps the biggest of all, I would say. Lots of data science problems are classification problems. But classification problems also arise in search for explanations, in science, you could say. So here I list just a couple of examples from my own research that I know of. Genome-wide association studies. That's very typical in bioinformatics, where you have measured the genetic quantities, you could say. You quantify the genetic information in some way, and then you want to understand how this associates with different classes. For instance, you have persons that have some disease and some other persons who don't have this disease. Can you explain why the diseased persons have the disease just from looking at the genes, right? That's a very typical example of a classification. And then the response is categorical, right? Either you have the disease or you don't have the disease. There is no sort of degree of disease. Either you have it or you don't. Another example here, which bacteria are more or less abundant in natural versus polluted environments. That's something I do these days. And notice here we have sort of environments categorized, either natural or polluted, right? Two categories. In both these examples, there are two classes. Classification problems may easily have more than two classes. It's not like it has to be two. Can easily be 3, 4, 5. But this was just some examples. We will see that. Multivariate data. Yeah, I should say a few words about why we should look at this, at classification problems in a multivariate way. And this is a sort of a classical example that illustrates this. So let's say we now have these two classes, healthy and diseased, and I even color them differently, right? And let's say we now have only two predictor variables, and that's simply because I'm going to make a drawing. We could, and we typically have more than two, right? We could have even super many if it was like genes or something. But let's say we have two. And then we can actually plot into a two-dimensional diagram here, right? Where we have x1 axis and x2 axis. So let's do that now. x1, x2, where are our data cases? Right? So let's say we have measured some healthy and some diseased people, their x1 and x2 values. And let's say we focus on the x1 value first. And here we have the people that or the results for the different people, the different persons we have measured. And we see the healthy ones are the pink and the green ones are the diseased. And as you can see here, it doesn't look like x1 carries any information about this disease, because we can see that the low value here is a healthy one, but the next one is a diseased one, and then there is a healthy one again and a diseased one. They are sort of completely mixed with each other. If this was a very good sort of powerful variable for classifying these two, then we should see all the healthy one on one side and all the diseased one on the other side, right? Then we can say, okay, if you have a big value here, you are diseased, right? Or opposite, if you have a small value along x1, you are diseased, right? You're not healthy. So that would be a very discriminating variable, as we say. A powerful information, contains a lot of information, right? But it doesn't appear to be that here, because everything is mixed. If we look at the second variable, it looks almost like the first one, right? Again, these are mixed, healthy and diseased. So it doesn't look like this one contains any information either. None of these two tells us anything about who is diseased and who is healthy. Well, that's wrong. Because if we now plot the two together, so here we have the dot for this person, right? Which has this x2 value in combination with this x1 value. That's this person, right? If we combine x1 and x2 together. And this one has this x2 value in combination with this x1 value. And so on, right? So each dot here now has an x1 and x2 value, and I colored them by the same colors. And now we can see how super good these two separate the green and the pink group. And the point with this is to illustrate that even if x1 alone is not very informative about disease, and x2 alone is not very informative about this disease, these two together can be super informative. Perfect separation here between the groups, right? If you have a big value of x2 and at the same time a small value of x1, right? You are on this side of the blue line, then you are healthy. If you are on this side, you are diseased. So this is an example of how we sometimes can find patterns if we do things multivariate, if we use all the predictors at the same time and not look at them one by one by one. So looking for explanations in one by one variable is perhaps a little naive, right? You would never see this then. So we should use methods that are multivariate. They take all the predictors as input. The base classifier, and this is sort of the theoretical fundament now for this LDA method and many other classification methods. I would say this is sort of the main idea from the start, I think. And it's sort of an optimal classification rule that guarantees maximum accuracy if the presumptions hold, right? That's typical for all these methods, right? You make some assumptions, and if the assumptions hold, then we can guarantee some optimality. So how does it look like? Well, first of all, for each class C, it's either 1, 2, up to this capital C classes, right? Remember, we have capital C classes. So let's consider one class now. Compute then what we call the probability of the class given the data. That's how you should read this. So the probability that our response number I equals class C, given that the predictors are exactly as in data case I, right? Probability of class C given the data xi. Yeah, so this is the data case row number I in A. So if you have computed this one, then for the given xi, we have one probability for each class, right? Because you do this for the first class, for the second class, third class, and so on, depending on how many classes you have. And then you have this probability, and then the base classifier says, assign to the class with the largest probability. So if you can compute these probabilities here, then you have what you need to classify. You simply classify to the class having the largest probability. And that makes sense, right? Why should we not do that, right? The problem lies in computing this one. But as soon as you have some estimate of this one, here is the base rule. So how do we actually compute this conditional probability here? Because it's a conditional probability, right? Probability of the class condition on the data. So that's what we will see now, one way of doing it at least. But before we start on the LDA, let's talk a little bit more about the theoretical fundament here. Prior probabilities is something we hear from time to time. What is this? This is the prior probability of class C. And notice there is no excess involved here, right? There is no excess. There is one prior probability for each class, and this is the probability of observing the class without any other data available. So we know nothing about the world around, you could say. We know nothing about the excess. What is then the probability that the next Y is of class C? So this is then based on existing knowledge about the classes. And this is something we very often have, right? Because, for instance, if the classes were diseases, right? We have some idea how frequent disease is. If you sample like 1,000 people, how many of them, or how big proportion of them do you expect to have this disease, right? It's not like 50%. Unless it's an extremely common disease. It's often very small, right? But so it's not unusual that we have some information about what we call the prior probability. What is the probability of each class before you start measuring anything about this data cases, right? That's the prior. If you have no such information, you typically use what we call a flat prior, meaning all prior probabilities are the same. So you simply say that this prior probability is 1 divided by capital C. So if you have two classes, it's a half for each one of them. Both are equally likely, right? So this is used when you have no other information. And that's reasonable, right? Then you start out with everything being equal. what you should be aware of is that many data analysis methods will use what we call the empirical prior. Because once you have a data set where the response are assigned to the various classes, right? Then you will have a proportion of each class in that particular data set. And this is actually the empirical prior, the proportion of each class in your current data set. And this is very typically used by default in many methods. So be aware. I mean, you may have a data set which is very skewed, right? You haven't sampled equal amount of all classes or the sort of the correct proportion of each class. Your data set can easily be skewed. And this will then be a bad prior unless you override it. We will see how to do that. But I mention it because this is default behavior in the methods we will look at now. And unless you are aware of it, you will always use the empirical prior, which may, in most cases, it's okay, right? Because if you have a fairly big data set, the classes should be represented more or less with the proportions that they are in real life. Also, we typically use this symbol pi c for the prior for class C. And notice this has nothing to do with the number 3.14. It's simply the Greek letter pi used as a symbol, like any other symbol, right? So it's just a mathematical convention that this Greek letter pi is used in this context. So I will do it as well. It has nothing to do with 3.14. Posterior probabilities, yes. The Bayes theorem, and this is something you should know about from the basic statistics course. And if you don't, look it up. It's easy. The Bayes theorem says, if you want to compute the posterior probability, as we call it, the probability of a class given the data, you can do that by this formula here, by having the probability of the data given the class. Notice how this is opposite of this one. Right? Here you have the probability of this one, given that this is the case. Here you have the probability of the data given the class. And then you have the prior probability here. You recognize it from the previous slide. And here is then what we call the probability of the data. And this is what we call the posterior, this one is the posterior probability for class C. And this is the one we should have, right? According to this Bayes rule. Once we have this, we have the solution. Then we just classify to the class with the biggest posterior. This one here that you see up here is what we call the likelihood. This is the likelihood of the data given the classes. So it's the probability of our data given the classes. Yeah, this is the prior, yes, I mentioned, same as we saw in the, and this the denominator here is the probability of the data. And this is a tricky one. But notice, for each class C, the denominator becomes the same. Right? Because there is no information about class C here. So this is actually, and we want to compute this for different classes, right? For different classes. And then the only thing we have to change in this fraction here is the numerator. The denominator becomes the same. So actually, and since we are not really so interested in the size of this probability here, but which one is the biggest? For which class is this the biggest? And then of course, the one with the biggest numerator will also get the biggest here because they are all scaled by the same denominator. So the maximum probability means the maximum numerator up here. So the likelihood. For each class, 1 up to capital C, The data cases are sampled from some probability density, right? So imagine now we have only one x. That's the easiest to start out with, right? One x axis. And then we say, okay, if you are in class number 1, the x values tend to be on this part of the x-axis. If you are in class number 2, they tend to be in a slightly different part of the x-axis, right? And with some probability density function here. So we can actually say that this likelihood can be written like this. It's a probability density function for a new one for each class, right? And this means the joint probability, if you not look at the conditional probability, but the joint probability, probability of having this X data together with this class, not conditional, but together with, simultaneously with, that will be simply this here times the prior probability of each class. And this follows from the basic relation between joint and conditional probabilities. Look it up in STAT340 or introductory statistics. The relation between joint and conditional probabilities. This one follows. And then we can compute the marginal, as we say. The marginal probability, the probability of this here, when we sort of integrate out this other information in the joint probability. So that's why we instead of integration, it's a summation because it's categorical, right? So we sum this over all classes and then we get this sum here. So we actually have an expression for this one here now. For a given data case, we can now classify to the class C having the largest posterior, where the posterior is now, this is copied from the previous slide, and now I just rewrite it in a new way, right? We have the function, the density here, describing the likelihood, as we saw up here. We have the prior probability written as this pi c, and now we have this probability of the data as this sum here, written from here. So this becomes the fraction we want to use. This we want to compute, right? So we need the likelihood, the prior, and this one here follows then also from the same, right? Can you see that? It's just a sum. So if you have this f of every c and the pi of every c, the rest follows. Linear discriminant analysis, what is this? So here we now look at a method that uses one idea of how the likelihoods should look like. All likelihoods are multivariate normal densities with the same covariance matrix for all classes and with unique expectations for each class. Okay, so what does it mean? It means that these likelihoods are normal distributions, and each class has its own sort of location, you could say, the expected value in the normal distribution, where the top of the distribution is located along the x-axis, but they all have the same spread. They all have the same width. That's common to them all. That's the assumptions of LDA. So an example, if you have like 2 classes and 1 predictor, and that's the easy situation to start out with, it would look like something like this. So here you have now the x-axis, right? This is only one of them, only one x-axis. And here the pluses here are the data cases, right? And we can see there is now a red and a blue class. class 1 and 2 are colored red and blue here. We can just call them class red and class blue. And then, since our data are supervised, right, we know which are the red class and which are the blue class in our data set. And here we can see a typical example of a very nicely discriminating variable. The X variable discriminates very well between red and blue classes because all the reds are down here and all the blues are up here. Right? So we have a perfect separation actually if you draw the limit here somewhere. And then the LDA method says, okay, the red dots, crosses, pluses are sampled from one normal distribution with a center around here, which is the mean value for the red ones. And the blue ones are sampled from another normal distribution with the mean here, which is the mean of the blue data. But they all have the same spread. Whether you are in red or blue class, the width of the normal distribution is the same. So they have the same shape, right? But they are located at different locations. And then you will get the separation between the classes exactly here. Yeah, okay, that's not really necessarily true. We will see in the next slide. But at least these are the likelihoods that are assumed by the LDA, normal distributed likelihoods. And this is of course not always the case. This is just an assumption, but it turns out to work pretty well in many cases. Data are normal, the X data are normal distributed, right? So the LDA posteriors, how will they look like? Okay, if you have now a flat prior saying that the probability of red and blue is 1/2 in both cases, then the posterior will also look exactly as the likelihoods, because then you say both are equally likely. So the size of this, the probability under this curve here should be the same as the probability under this curve here. They are both scaled with a half, so the area here is 1/2 and the area here is 1/2, and together they are 1, right? And then we can see that decision boundary is here, the separation between the classes, because if you are on this part of the x-axis now, the red probability is bigger than the blue. Remember the base rule, we always classify to the probability which is larger. So if you go in here, x equals 120. The probability of being in the blue class is pretty small, right? While the probability of being in the red class is much, much bigger. So then you would classify to the red. But if you go in here at 140, okay, now the probability of red is very small, but probability of blue is very big. So now you will classify to the blue. And then you can see here, exactly here, they are equal, right? So here you cross the decision border. So if you are to the right here, then blue wins. To the left here, red wins. That's the base rule. So what if we have different priors? Let's say, okay, the red class is actually much more common. 4 out of 5 cases are red, while only 1 out of 5 is blue. This is something we know from before. So disregard the number of observations we have in our dataset. Use this information instead as a prior. Red is much more common than blue. Then you can see that the likelihoods are scaled differently. So now this likelihood, the red likelihood, is now multiplied with 80%, right? 4 divided by 5. So this area is now 0.8, while this one is only 0.2. So the blue becomes much smaller. And notice now how this also changes the location of the border. So up here, the border between them was below 130. But now, since the red, we know that the red is more common than blue, then the border is pushed in the direction of the blue. So the red one is a bigger class now, you could say. Over here is the difference now. You need to be further up here in order to be classified as a blue, because we know that the red is more common. So this is how the prior probability sort of scales the likelihoods and thereby shifts the classification, the decision border, as we call, where we shift from one class to another. Okay. If you have more than one X variable, then of course this is more tricky to draw. Here I have just copied some drawings from that book that I mentioned initially. So here you can see we have two x1 and x2, two columns of X variables, right? And then you get sort of, instead of you have the normal distributed sort of mountain, right, in two dimensions now. And the covariance matrix, the shape of it, the covariance matrix determines the shape of the likelihood. So here we have a mountain which is where the spread in both directions is the same and there is no dependence between them. Then the mountain becomes sort of round, you could say. If you see it from above, the height curves will be circular. But if there is a dependency between the two variables, the mountain will be sort of flattened in some directions and wider in some others. Right? And this we should be familiar with this from PCA, right? Because in this setting we would now find the principal component along the wide direction of the mountain. Right? So remember this, that the shape of this likelihood function is determined by the covariance matrix. And the expectation is where it's located. Okay, so that's where the top is, right? So if you have two classes, they will have two mountains, right? And they will look the same, but they will be located in different places. And the decision boundaries always become straight lines with this LDA method. So here we can see another drawing from that book where we also have two predictors, and now we see it sort of from above. So you can think of this as these contour lines, right? So here we have three mountains now, right? A yellow, a blue, and a green. And we have drawn only one contour line for each one of them because they all have the same shape, right? But they are located at different places. This one has a top here, the yellow one, the blue one has a top here, and the green one has its top here. And then you will see these black broken lines indicate now the decision boundaries, right? And you can see the background has been colored by the same colors. So if you are somewhere in the yellow region, the yellow mountain is the highest one, right? Has the biggest probability. And over here it's the green, and over here it's the blue. So the decision boundaries are always straight lines in LDA. That's amazing. But that's nice. Quadratic discriminant analysis. What is this? What is different? The only difference to linear discriminant analysis is that we now allow each covariance matrix to be unique. Each class has its own mountain, but now the shape of the mountain is also unique to each class, not only its location. And then the decision boundaries become parabolas instead of straight lines, so they become curved. And that's why it's called quadratic discriminant analysis, because the parabolas are functions of quadratic functions, right? And that means you can, in some cases, get what we call disconnected regions. It could be that you have the same class occupies two disconnected parts of the space. So it can be the winning part in one region then a losing part in another region, and then a winning part again in a third region. Winning class. So why not always QDA rather than LDA? Because this is more flexible, right? You allow each class to have its own likelihood, right? The shape of the likelihood is unique to each class. Well, the reason is that this requires a lot of data. So if you have P predictors, and P can sometimes be quite large, right? Then there are P times P plus 1/2 parameters to estimate in a covariance matrix. This is a lot, right? And for LDA, you have one such matrix. But for QDA, you have one for each class. So you need a much larger number of observations to get good estimates of a covariance matrix. So you need at least these many observations to get estimates of one covariance matrix, right? And that's usually possible with LDA because you only have one such matrix. But with QDA, you have one for each class. So you need a lot of observations for each class. And it's not enough to have a lot of observations in total for QDA. Notice that. You can have millions of observations for one class, but if you have only 2 observations for another class, you are lost. Because you need many observations for each class. And that is the limit for QDA. But if you have a lot of observations, if you have a lot of data, large N, QDA will usually win over LDA, right? Because it's more flexible. So again, we have this problem of overfitting, right? QDA, if you don't have enough data, QDA will be an overfitted model. And then you will stick to LDA. Okay, we will have a look at this in R now. So let's have a look at the linear discriminant analysis using this lizard data. Yeah, the lizard data is some measurements on lizards, and the lizards come in 2 sexes. So that's the classes. Let's have a look at it. I copy this and paste it into my week 10 script here that I have. So let's load our R package and this dataset lizard. So here we can see the classes. There are actually only 2 classes, female or male lizards. And these are now the response. And we want to see, can we classify this lizard sex based on some simple measurements of their body. And that was the drawing. The first is just the weight, right? The mass, that's how much the lizard weighs. And then there are some length measurements here, SVL and HLS. Yeah, you can see here where snout went length. Yeah, that's the SVL, the length from the tip of the nose to back here. Yeah, and then hind limb length. Yeah, that's the length of this. Yeah, some of there are apparently some other measurements who are not part of this data set, so we only have these 3. But okay, that's big enough for our example. So let's see how we do LDA on such a data set. And the fitting of LDA is really simple. First of all, you need to load this mass package. You don't really need to install it because it's always installed as one of the base packages in R, but it's not loaded, so you have to library it like this. So let's do that. That's where we find the LDA methods. And then the method for fitting an LDA model is simply the function LDA. And notice we specify now the model just like we have seen before in LM or in LME or the other methods that we have used. So we have the response, the name of the column with the response, right? And then this tilde operator, and then simply the variables we want to use as as predictors. And here we use all of three of them and then specify which table is the data table. So let's fit this. Okay, then we get an LDA object. So we can now inspect this LDA object. Let's do that. Let's click it open here. Then we will see it contains a lot, but let's focus on only the basic ones here. First of all, the prior informations, and notice this is now the empirical prior, and this I mentioned in the lecture. So if we look at it here, prior like this, oops, LDA. We see that the probability of male is a little bit bigger than the probability of female, and that is simply because in our data case there were 25 observations, so we couldn't have the equal number of both. So this means we think that males are slightly more common than females. I suppose they are not. I think that it's reasonable to assume that the sexes are of equal numbers. I don't know anything about this lizard, but anyway, we would question the use of an empirical prior here. I think I would require a flat prior. Say that, okay, both sexes equally likely. We also have here the means. So if we look at LDA object, the means. And here we now have the mean value for the two classes, right? The mean, the center or the top of the mountains, you could say. So if you are in the male class, mass should be like this, SVL like this, and HLS like this. So these three values now form the top of the mountain in a three-dimensional. We cannot really draw it, but we can imagine this is sort of the top of the mountain in a four-dimensional drawing of the male mountain, and here is the female mountain. And we can see they are slightly different. The masses are smaller for the female. These SVLs are also shorter for the females. And also the HLS are smaller. So all these three measurements that we make here now are typically smaller for females than for males. So the two mountains are located on slightly different locations, but they have the same size. Yeah, I don't think we will look more into the details there, but just have a look at how we can change the prior if we want to refit our model without using this, using a flat prior, right? Notice also, instead of summing up all the other predictors, you can just use a dot, right? If you have many predictors, this will be a very long list to write, right? So then you can just write a dot, and that means all the other variables except this one in the data table. So that's convenient. Notice also how we now specify the prior here. So the prior for the two classes is 1 divided by 2 and 1 divided by 2. So it's a half, 1/2, right? So here you can now go in and specify your own numbers, or we could have just written like this, of course, without dividing by 2. Feel free to do it any way you like. So if we fit the object like this and then inspect it, now we will see the priors have changed here to 1/2 for each. So we override the empirical prior. We can also predict from this object, and that's very convenient because that's give us the classification really. And notice now, predicting, it's not really predicting because we use actually the same data. We use this predict function, and this one can be used for all kinds of data or fitted models, right? Also for fitted LDA objects. We have used it for LM and LME and all kinds of objects. And it works also for LDA object. So then we just take the fitted LDA object and nothing more. If we do that, let's do that first. So what is this pred LDA? If we look at it here. Yeah, it contains three sort of informations. The class, and this is actually now the predictors. So let's have a look at that. Pred LDA $class. So here we now have the predicted class for each lizard, right? And this is based now on the fitted LDA object. This is how the classes should be if they obeyed the LDA model completely. So don't confuse this with the actual observations for each lizard. This is the predicted based on the fitted model. You can see there is also posterior here. Yeah, and we should inspect that as well. So let's pred LDA, because these are actually the posterior probabilities, and now we have one for each class, right? So for the first lizard, this is the probability of being male, and this is the probability of being female. And we can see that this is super big. It's 99%, and this is almost 0, right? So the first lizard, according to the LDA fitted object, should definitely be female, right? That's why it's classified as F here. The second lizard, this is a super big probability of male and a super small of female. So this is definitely male. And that's also why it's classified as male up here. Right? So, I mean, this is the sort of the classifications, but this posterior probabilities gives you now sort of the detailed information behind the classification. So here you can now see if a classification is very close to the decision border, then the probabilities are almost 1/2. Are there anyone? I can't really find any. I think this lizard data are so sort of good in the sense that they are, yeah, I can't really find anyone here which is very close to the decision border. If the data set is sort of very easy to classify, you will not find anyone. But let's say there were a lizard where there were almost 1/2 in each direction, right? It's like 51% male and 49% female. Then it's classified as male, but then it's a very uncertain classification, right? So looking up these posterior probabilities is a way of evaluating the uncertainty behind each classification here, because if it's very close to the border between the classes, it's of course very uncertain. But it doesn't appear to be anyone here. It looks to me like all of these are very certain classifications. No data points are on the border. Okay, so the QDA then. How do we fit the QDA model? And let me just copy this. It's super simple. You simply replace LDA with QDA and everything else is as before. There is no difference. So you simply fit the QDA object and you predict in the same way and you get the same, oops, sorry, over here. Let's QDA posterior, like that. Yeah, similar for the QDA, exactly the same type, or the classification, right? But the results may of course be slightly different from the LDA because it's a different model, right, for the same data. When it comes to the prediction here, I should actually mention that what we typically use this predict function for, perhaps, is for new data. If you have new data, how would you do that? Well, let me just show you here and now. if we really have some new data, then we have to specify new data equal, and here we now have to have a new data frame with some new values. So let me look up into the original data frame here. Okay, so let's say we have a lizard now where mass is 5, SVL is 60, and HLS is 110. Right? Data frame, mass is 5. What was it? SVL 60. And the last one, HLS 110. Like that. Notice that you have to create a new table having exactly the same column names as the original, the training data that you used to fit the object up here, right? The lizard data. The predictor, the X's, the predictors have to have exactly the same name. And of course their values can be wildly different actually from the data you fitted with, but if they are super different, then these predictions will be really strange, right? So if I call this pred2 and pred2 LDA class, then we will have a classification. This was classified as female, right? Or we can look it up with the posterior. So now you can experiment or have some new test data, right? That was never part of fitting the model, and see how these are predicted. What is a good model? So we need some test data in order to verify it or to say something about this, where we know the true class, but then we predict the class as if we did not know. And we just saw in our session how to predict in a situation like this, right? So once we have this, then we can compute what we call a confusion matrix, because now we can actually compare the predicted classes to the true classes, right, in the test data. And the confusion matrix, what is a confusion matrix? It lists how many data cases in each possible outcome. And for C classes, this is a C times C matrix. So you have one row and one column for each class. And then it lists how many are how many of the true classes are actually predicted, and so on. So here we have an example of a 3x3 confusion matrix where we have 3 classes. I'll call them A, B, and C here. And then you can see, yeah, one of them is the predicted and the other dimension is true. And here is the true are in the columns, while the predicted are in the rows. I mean, this could be reversed, but I think this is a convention. You just have to know which one is which, which is the true. So it means that from class A, there are actually 13 observations in this data set, because if I sum 10 plus 3 plus 0, 13 are true. So of the true class A, there are 13. There is actually 9 of class B, and there are 12 of class C. That's how I should read this table, right? When it comes to the predictions, they are now spread out according to how they match the truth, right? Because notice in the test data, we have the actual true class, and then we make the predictions as if we did not know the true class. And then we can see in 10 of the true A's, we also predict it to be A. In 8 of the true B's, we also predict it to be B. And in 11 of the true C's, we predict it to be C. So the green numbers here are the correct classifications on the diagonal. The red ones are the mistakes. So we can see here in one case, this this observation should actually, it is actually of class B, but it's classified as A, predicted as A. So this is wrong, right? And here we have 3 mistakes. A's, they are actually A's, but they are predicted to be B's. So here we make some big misses, more mistakes, right? And then we have another mistake here, and in C we never mistake. So all the predictions of C are correct. So the accuracy is simply the proportional correct. The sum of the greens divided by the sum of all. And that's, or the sum of the diagonal elements divided by the sum of all elements, right? The larger the better, of course. The posterior mean is almost the same thing as the accuracy. Remember that the posterior probabilities are indicating how certain you are of each classification, right? So instead of simply counting if you are wrong or right, you can sort of add up the posterior probabilities for the true class in each data case. And if this is sort of big for the true classes in each case, you get a big posterior mean, right? And that's good, because then it means that you are certain, you give sort of certain predictions of the correct classes each time. So this should be as large as possible. So it's not a simple count, right? Because if you then have some very uncertain classifications, this will be reflected a little bit more in the posterior mean. I should say that the accuracy is by far the most common measure to use. And I mean, if you have a lot of data points, large N, this one is more than good enough. You will not get much improvement by looking at the posterior mean. And I mean, for LDA and QDA, you can do this, but for many other classification methods, you don't have these posterior values. And you always have the classifications. So that's why this accuracy is a more common measure, because you can sort of compare it across different methods easier. Okay, cross-validation, we have seen this before. If we have no separate test data, we may use cross-validation. We have done this before, right? And the procedure here is exactly the same as for regression. You leave out some data cases as a test set. You fit the model to the remaining data cases as a training set. And then you predict the test set classes and compute accuracy. And this, we did exactly the same thing in, I think it was in week 7 for regression, where we, week 6 or 7, I don't remember. We computed this RMSP or RMSE, I think, root mean square error. Yeah, or mean square error. I remember we did it slightly in 2 different ways, with or without the square root. You can look it up. But it's the same. But now instead of this one, because we don't have numerical responses anymore, we just compute accuracy, as we saw in the previous slide, as a measure of goodness, right? And then we of course repeat this until all data cases has been a test set once. So that's cross-validation, right? You leave out some data, train on on the data you have behind, predict on the test set, and then you simply just do this over and over and over again until all the data has been test set once. Then you have the final accuracy. So this is easy to do. Let's see how we can do this in R. So let's first have a look at how we can compute the confusion matrix, because we already have some predictions who are not really predictions, right? Confusion matrix. Let me just... So above here we made some LDA predictions, but we actually used the same data, the training data, right? As we had used for fitting the LDA object. We used all the lizard data, and now we just use them again and make a prediction. But it's still possible to compute a confusion matrix, even if it's not strictly correct to call this a prediction because we reuse the same training data. But let's do it anyway because it allows us to compute the confusion measure. We need this mix-lm-r package that we have used before as well, so you should already have it installed. And then there is a function called confusion. And notice the input. First we give the true classes, right? And these are the true classes because this is now sort of our test set, right? Which is the same as the training set, so it's cheating, but these are the true classes. And then we have the predicted classes here, right? We saw that previously, how the class column in that, or class variable in that prediction object. So let's compute the confusion measure. I don't store it, I just output it directly on the screen here. I could just as well have stored it into an object. But now we can see it list the true classes, male or female, in the columns, and the predicted classes, male or female, in the rows. And here we can see the content, right? We see that 13 out of 13 males are classified as males, and 12 out of 12 females classified as female. So this is a perfect classification. Can you see that? The accuracy is 100%, because all the values are on the diagonal. So that's almost too good to be true, right? And it's actually too good to be true, because this is not really a prediction, right? We cheat here because we use the same data that we used for training as a test set. So, but it tells us how to compute. So we can do exactly, of course, the same for the QDA. No, sorry. We do the same for the QDA and get a similar. And here we make actually one mistake. Can you see that? So now it's only 96%. This is still super good though. And you can see there was actually one female, should have been female, that was classified as male, predicted to be male. So that was the only mistake now. So QDA was actually poorer than LDA here. And that is probably because we don't have enough data to fit the QDA model properly. Okay, I don't think I will do this posterior mean here. You can do it yourself, computing the posterior means. Let's turn to the cross-validation instead, because both LDA and QDA actually have options for doing this, so we don't really need to code anything ourselves. We can do the cross-validation. If you remember, we did this for this PLS and PCR and stuff as well. They also had these options for doing cross-validation. So here you can see we fit a new LDA model again, using the same data, the same prior, but now we set CV equals true. And this will now do what we call a leave one out cross-validation. I think we saw it earlier, meaning that each single data case is used as a test set. You fit the model to the remaining data cases and then predict the last data case. So let's run this. And so now we don't fit a single LDA, but actually we fit one LDA model for each new data case and use that data case as a test set. So if we run this, it doesn't take much time, but of course if you have super big data sets, this can really take some time now. Let's have a look at this object here. How does it look like? It's not entirely similar to the original LDA object, right? If you look at the original LDA object, contains more information in a sense, but this one contains now the classes that were predicted, and that's important. These are not the classes you get by simply using the training data, but these are the classes you get by cross-validation and prediction in that sense. And these are the classes we now will use to compare against the truth. So now we compute the confusion matrix with the same truth as before, but now we use these classes instead. And this is a little bit more, this is sort of real predictions. This is real predictions. And now we can see actually we make exactly the same mistake as QDA did previously. So, and that's quite typical, right? That the accuracy you get by cross-validation is a little bit poorer than if you use the training data directly, because yeah, it's more difficult to actually predict than just use the training data as tested. So this is the one we should use. This is the accuracy that we should use to evaluate how good this LDA model is actually. The cross-validated accuracy instead of the one we computed up here, because it's sort of cheap. This will easily lead to overfitting if we base our model selection, we will see shortly, on this one. We should always base it on the cross-validated one. Or if you have a separate test set, then you do as we did up here previously, like this, to get new classes, right? But leave one out. Cross-validation is always an option. Finally, some words about variable selection. Which variables have discriminating power? This is typical a question we will ask ourselves in the setting of STAT340, because we want to understand which of the predictors are important for discriminating or separating the classes, right? Which variables carry the information about classes. And remember the multivariate setting that we saw previously, that we should actually do this by considering all variables simultaneously here, right? This is quite difficult for more than two classes, because some variables may be important for separating, for instance, class A from B, but some other variables may be important for separating class A from C. So it's not really straightforward to find the variables who are important for all classes. So what we may do here is to break this into many two-class problems. So instead of looking at all, if you have three or more classes, instead of looking at all classes simultaneously, you can fit LDA models to such data. But when it comes to finding the important variables, it may be a good idea to actually break it into several two-class problems instead to do this, because of this problem here, right? And an example of finding the important variables is to use best subset selection based on cross-validation that we just saw. So best subset selection, and that is exactly what we will have a short look at here now at the end, how to do that with LDA. Okay, so let's have a look at the best subset selection procedure, and here I will code it in detail actually, because there is no, or there, I suppose there are, but I haven't directly found implementation of this. But it's not very difficult to code ourselves. So in the listed data we have three predictors, right? Which combination of these has the largest discriminating power? Or are there any one of these we can throw out, we should say, right? Do we need all the three predictors, or could we do with two of them, or perhaps even only one of them? That's what we want to investigate now. So we want to fit models of different sort of, using different combinations of these three predictors and see what comes out the best. So first of all, we need to make all the subsets. And what do I mean by subsets? The subsets of variables now, not the subsets of rows, but the subsets of variables. Subsets of variables, right? What type of submodels actually we should use? I should actually, I think I would actually call it submodels. No, I will. I will stick to the name used in that. But I think I should. Submodel would have been a better word here. So this function here, expand.grid, what does it do? Let's run this code first and see what it does. And notice I gave it as input 3 vectors. Both are true or false. This is a vector of true and false, another vector of true and false, and another vector of true and false. And why 3? That's because we have 3 variables that we want to combine now. So this is one way of doing it. If I run this one here and then inspect this subset data frame, it becomes a table. And here you can see it now creates all the combinations: true, 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 false, true, 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 false, true, false, false, true. These are all the 8 combinations you can have of true and false here now. And notice the last one is false, false, false. And that one we don't really need, because we don't need a model, or we don't want to have a model without any predictor. But anyway, we now put some column names. We don't really have to do that, but that's convenient to use the column names so that we can actually recognize which column correspond to the 3 variables in our original lizard dataset, right? Here we have the 3 predictors. This is the response, but these are the 3 predictors we now want to investigate. Which one of these can we do without? And then we have now 8 different sort of combinations of them, but the last one we don't really need, so I will take that out. Yeah, that's what I do here. First I add another column here by mutating into the same column called accuracy, and I put it to 0. So let me run that one so you can see that, whoops, we cannot find mutate. No, of course, because we need to load the tidyverse. I had forgotten that in my code. The tidyverse is needed to use the mutate column. Now he mutated it in the accuracy column here, because we will fill in some values here now soon. And then I take away the last observation. I slice out everything except the last. That's what this means. -n means slice or keep all rows except this row, which is the last row. So I run this one, and then you can see we have only 7 rows left now. So now there is at least 1 true in each row. So here we now have all the submodels. The first one is using all 3 predictors. Here we only use these 2 predictors. Here we also use 2 predictors. And here we use only this predictor. Here we have 2 predictors again. And here we have this one only, and here we have this one only. So now this should now ensure we have all combinations. So then we do the cross-validation, and then we need a for loop here, because now we need to do the cross-validation for each subset. Submodel. So you can see for each row in that, from 1 up to number of rows in that table up here, we now say use the columns which are, and if you use the which function, you collect the ones who are true. So in the first round we will use column 1, 2, and 3 because all of them are true. In the second round we will use only column 2 and 3 because these are the true, right? In the third round, we will use column 1 and 3, and so on. So this is where we now sort of decide which columns to use. And then here is a slight trick, because we can actually, when we fit a LDA model, we can specify the input in a slightly different way to what we did previously, because previously we used this formula, right? This one. We use this formula that we are used to. The response and this tilde and then the predictors, in this case all of them. This is an alternative way of inputting it. So LDA allows you to input first a matrix or data frame with all the predictors, and then specify as grouping which is the category, the response, right? Which is the response? Which one of these are the response here? So this becomes nice now. No, it's not part. I mean, you can see here that this X contains only the predictor columns. If you wonder why I have to put this drop equals false here, that's because if you select a single column from a table, it will no longer be a table. It will just be a vector. But if you put this one in, then it's still a table of a single column. So this should be a table now containing 1, 2, or 3 columns, depending on which iteration we are in here. In each cases, we use this as the response, and the rest of the model is as we saw before. Sorry, the rest of the specification here to LDA. So we get an object here now, and then we use this computer accuracy, and I don't use the confusion function because I can do it directly, right? I can just take the true classes compared to the predicted classes, and this will, the double equal sign means you compare, so this is either true or false, depending if they are the same or not. And if you sum up true or false, you get the number of truths. So this is actually the same as the sum of diagonal elements in the confusion matrix. And then I divide by the total number of elements to get the accuracy here. So let's run and see. And this takes almost no time because it's only a few rows, right? And each fitting of the model takes almost no time. So this is super fast. And then we, of course, look at this resulting subset, or we can actually inspect it here, because now we can see we have filled in with some accuracy values here along the line. And then we can actually just arrange an output like this. Arrange function will sort a table, the rows of a table, according to some column. And if you only specify the name of the column directly, it will be sorted in ascending order with the smallest value first and the largest value last. But we want the opposite. We want to have it in descending order, and then you write it like this. So we have the largest value first. And here we can see how it turned out. And actually the best accuracy from cross-validation is found by using only this variable. And that's amazing. We don't really need the other measurements. You can predict the sex of this lizard by only this measurement only. This is the perfect variable. This one gives you all the information you need according to LDA. So that's how you do cross-validation and best subset selection. I should, before I finish, just of course mention that if you have very many predictors, if we had a lot of columns, this way of doing is not really a good thing. And that is also the problem with subset selection, right? Best subset selection. If you have too many predictors, there will be an enormous amount of subsets, right? Submodels. So this is only useful for a smallish number of predictors, I would say. If you have really many predictors, and I think we will see that in an exercise this week, then we will have to do some principal component analysis or something like that in combination with LDA. And I think one of the exercises is looking into that.